I'm now going to measure and discuss more in a general sense these transducers, the ultrasonic range finding, the piezo crystal itself as measured through this fixture, the ultrasonic cleaner, the buzzer, and the speaker. So let's get started on that. So first up, the range finding transducer, which we've already measured that before, and we already calculated the equivalent circuit for it. But in this case, I'll just let's measure and let's talk. Notice this delay time here. It's quite important that your sweeps don't go too fast, or else you won't be able to, your instrument will likely provide variable and also incorrect data if you do your frequency sweeps too fast. So that's the 40 kilohertz resonance point there. And you see this other, what looks like noise on the phase. That's actually not noise. That is actually bending or other types of resonance in the structure, which aren't very well coupled, therefore you would hardly be able to predict them, but they still are the dominant, they still do exist as resonant modes. So here we have our initial resonance at 38 kilohertz, and then we have another resonant point. Stick that there. We have another resonant point here, and we can look at cursor 1 at 66 kilohertz, and also one here at 83. They're all likely related to that cone in this ultrasonic transmitter. We see in this case the resonance impedance is 384 ohms. Looking at the maximum phase being at about -50, we do see there's actually significant good coupling occurring given the structure. And the Q factor here is 38, which is low, but hey, it's typical of a bender. There's a lot of bending occurring. There was also bending occurring in the cleaner, some constraint and also some bending. However, the main resonance was still determined by that of the piezo, especially given the resonance frequency was similar to that of just the bare crystal. That's something I didn't show you. It's something I'm telling you. Let's take a look at measuring the piezo crystal as seen in the image right here. The crystal is about 10 millimeters wide, and we're going to find that its resonant frequency is quite high. We're going to be loading it into this sample holder held up by 2 pins, while the piezo itself is suspended at its nodal point in the center, which has little displacement. And we will also discuss its significance, and I'm going to move it too downward and show you what happens when you don't clamp the piezo at its nodal point. So let's go ahead and run our test from 1 kilohertz to, let's do 1 megahertz. Frequency steps of 1,000. And now we're measuring the piezo disc. And we'll load the regular settings of impedance and phase. It's the easiest to kind of visually interpret what's happening, although for specifics you'll need to go for real admittance and real impedance. So the phase is about -88, and here we have a resonance occurring. Now, in order to kind of get the view of the resonance, especially with the large range of impedance here, so I'm actually going to leave this blooper in here. The blooper was that I had the open circuit connection at 3.5 nanofarads and the compensation. And this is a different fixture. It's not the long BNC cable, which has much more capacitance than a simple sample holder. So what it actually caused was a very serious change in the response. So we have our piezo crystal, which obviously, we spoke about how it equates to the LCR circuit in parallel with a capacitor. But in this case, what happened was we assumed that this is the piezo here, and the calibration procedure assumes that there is a probe or a cable parallel capacitance that's added from the cable that's going back to do the measurement, the 2 terminals or 4 terminals. So it creates a capacitance in between these 2 leads. Now, if you overcompensate, like you do compensation with one set of leads and then you attach another set with, let's say, a lower or a higher capacitance. In this case, the new set had a much lower capacitance. I think the value that I last left off on was 3.5 nanofarads, which is actually quite high for this piezo material. And I'll just show a cool trick here, that if you measure a response from 1000 to 10,000 hertz, and then we do a compensation like we just pretend, and this is just kind of for demonstration. It's 4.41 nanofarads. Alright, so the compensation was before set at 3.5 nanofarads. And because you're compensating so much, what's actually going to end up happening is that this capacitor will be almost eliminated completely from the equation. So there will be almost inductive properties. So that you actually subtract the effect of the capacitance. So you assume that there's a capacitor in parallel, and you subtract out the complex current, which is the current occurring at 90 degrees. It's a negative admittance, or it's a negative impedance. Sorry. So it subtracts out that current that would have normally going through that capacitor. So effectively, starkly changes the response and increases the apparent coupling factor, and adds kind of a whole bunch of different flavor, skews the results significantly. So basically the takeaway is that if you don't get a resonant frequency pair occurring, then it's likely you either have not compensated, like if you get like a common thing seen with uncompensated circuits is a response like this. Or in the case that I was just showing you, it was instead of seeing a resonance anti-resonance pair, what we got was the resonance, but then we got something that kept going, and it peaked out here and it went back down. So there's different reasons why these phenomena occur. One of the reasons is this. Apparently, these are the pair from the measured data of the incorrect calibration. Because we actually subtracted that capacitance, the coupling factor goes way up because of this subtracted parallel capacitor. For this case, I'm just going to disable open circuit and short circuit calibration, and we'll go back to our 1 megahertz test range. So we have our first resonant frequency here, which actually corresponds to the radial resonance of the piezo material. You'll notice no low frequency modes, even though theoretically if you were to do modal analysis in FEA, or perhaps even do some calculations, hand calculations, you would find there are modes which exist in bending for the piezo, but due to the uniform electrodes, non-uniform modes are not excited. Non-uniform also includes bending and even harmonic resonances. So we see this occurring in odd modes. So we have 200, about 550, and about 890. They're not for a bar. These would be exactly they would be in exact intervals. However, for a radial mode, there are other distinctions which cause it to be not precisely 3 times higher than the original resonance frequency, but nonetheless, we can analyze it. So what, taking a procedure for characterizing a disc or a bare piezo element is different than a transducer, although you can analyze them in the same way. But in order to extract theoretical properties, like material properties, like the material coupling coefficient of the radial mode, or the elastic compliance properties, also the piezoelectric charge coefficient D31 from this, you'll need to apply other equations to resonance frequencies measured. Next, we'll go ahead and take a look at this ultrasonic cleaner here, which is a bolt-clamped transducer. And I'm also going to do an open circuit calibration because now we have a new system here. So I'm going to limit this analysis to 100 kilohertz. So that'll give me a good range there. So I'll go ahead and hook up the leads to the transducer. So we see several resonance frequencies. I'm going to reduce. So if you don't have kind of a given value for any one of these resonance or anti-resonance peaks, is having about 10 values on each in each case. So this is not nearly the resolution we would need in order to resolve precise resonant frequencies or quality factor. So you should at least have several points in between your maximum admittance, or in this case minimum impedance or maximum impedance, and the 3dB method if you're using the absolute values, or the half bandwidth if you're using real admittance or impedance. So let's just go ahead and reduce it by 1 factor. So we have a lower resonance frequency, and we have several other modes as well. So the main operating mode is at 40 kilohertz. These other modes here are either related to the bolt resonance. There are other bending resonance which occur, which are symmetric and are also antisymmetric or asymmetric. But this is a kind of a typical range. So what we actually do for analysis and characterization is we focus on one mode, and that's the 40 kilohertz mode here, because that's the operating frequency. We know that from the design. So we'll go from 38 kilohertz to 45. Just to get a better look at its response. And typically when we do these measurements, you don't want to constrain your device in any way. This is obviously not enough points. If you see the bottom frequency, it's in logarithmic. So we have an impedance of 20 ohms, and the next, we get to 54 pretty much past the 2 dB, 3 dB gain from that, and just one kind of step, frequency step. So we have to refine this further. It also won't take very long because for this specific transducer, we can identify the resonance and anti-resonance frequencies. The Q factor is 403, which is consistent with using hard PZT materials and with aluminum and components. There are spurious modes existing in this specific transducer, which is typically not a positive thing for bolt clamp transducers, having those modes there, but maybe have done to some prior use of the transducer. So this would be a perfect candidate for the normal method of that I mentioned for extracting material properties. If we had a harmonic too close to the anti-resonant frequency, we may just want to use the equivalent circuit as calculated from the resonance frequency to determine for example, the coupling coefficient. Instead of using anti-resonance, you can use the equivalent circuit. I just wanted to pause here and explain those spurious modes a little better. And the spurious modes did not exist in this transducer because of previous use or damage of another sort. If you see, there's this little bolt stuck in here, and I actually left that in there by accident. But this little bolt or nut actually comes out if you can pry it out, and it actually goes on the other side of the transducer, which helps to use it for mounting to a plate or a container that that contains the water for the ultrasonic cleaning. But I left it in there, and that condition of having this odd-shaped piece kind of jammed in the bolt there, that is what caused the spurious mode. So I've removed that. And now we'll go ahead and test again the same experiment. So we see no spurious modes, and I'll just do a step size of 10. So I'm just highlighting this specifically because, and we have a now Q factor of 800 instead of 400. I'm highlighting all of this because, well, things like this happen in practice, mistakes. in measurement. So you need to be careful in understanding if you're measuring your transducer properly, if there's not something wrong with how you're holding it, how it's being positioned, as we saw from the as we saw from the piezo crystal. Depending on if you don't hold it exactly at the center, which is the nodal point, you're going to significantly alter the response, and it can be to the point where you cannot interpret the values any longer. Here we would have incorrectly measured the quality factor, although probably during actual operation it wouldn't have mattered as much. But for these characterizations, you have to be scrupulous in determining if you are measuring your parameters correctly, and if there's something incorrect or something you didn't expect, like the spurious modes, that you go ahead and investigate that, and you look to remove those conditions which do cause that unideal behavior. So the next device we're going to analyze and take a look at here is the piezo buzzer. So I'm just going to attach it there. The way you shouldn't constrain your piezo material when you are testing. This can restrict movement and hence change properties and characteristics, and I'm going to show you that right now. So with this device, let's do 1000 Hertz to 1 megahertz. And now we are off to the buzzer. And let's do it a little bit faster so we can finish this run. You can obviously hear it at lower frequencies because that's in the audible range. So we see there are several resonant modes. They're easier to pick out in such a large scale with phase changes. So we see a mode closer to 1K, and then we see one, let's say at 20K and 100 kilohertz, and these phase dips and changes that are seemingly irregular. Those are indicative of modal activity, although they may not be well coupled, especially at this high frequency for this bending mode. So we don't see much activity past 100 kilohertz, whereas for the other disc, we see a lot of activity, a lot of larger resonant modes occurring up to 300, 400, I think even 880 kilohertz. That's because bending transducers don't have a high frequency response due to the excitation of high excitation of lower frequency bending modes. So whenever you cross resonant frequencies, you're in effect stiffening the structure, basically the reaction of that mode and bending modes in general don't react well as you start increasing in the mode number, like going from the first resonant mode of a particular type, let's say longitudinal or bending, and higher. Your coupling to your system is becoming less and less. So let's now focus on this 100 kilohertz. Well, actually, let's do 110 because that seems to be an area here, and also reducing the step size. You can obviously hear it initially. So this initial frequency is usually kind of the design frequency most of the time. So that, in this case, it's not the lowest resonance point, so it's not going to really show up there. But let's just manually kind of locate it there. It's 4,004 kilohertz. Then we have a mode at 30 kilohertz, 32, and several modes at 90. Bending modes can often couple with longitudinal or radial modes, which can create this what we call spurious behavior, where the peaks are irregular and there are many modes interacting with each other. So this is likely the first resonant mode here, and here is likely the first radial mode, and there's likely also some bending here. So this can this can be potentially another mode of operation depending on if your application will allow that behavior. So kind of let's get in a little closer to this initial bending mode, because it's going to be something which is significant for the use case of this bender. So let's kind of. So I just ran the transducer and it was sitting on my desk here, and now I'm kind of suspending it in air through the leads. And we're going to take another measurement. And notice that the resonance frequency was 4 kilohertz and 811 ohms. Running this again in air. Running this again in air causes a resonance impedance of 583 ohms. So it's different, it's less. For the bending transducer, again, you're going to have a low Q factor of 23 due to the epoxy bonding and losses existing in that motion and the energy transfer through the epoxy and that interface. So here we don't really have a clear anti-resonance. So let's dig into this one a little bit, because we see this clear resonance and anti-resonance in theory and maybe perhaps in textbooks, but getting to the meat of it and looking for parameters to reliably characterize. So we're kind of after two goals. The first goal is to capture the properties and also reliably capture them. So right now we have to set back the resonance measurements to real. So from the anti-resonant frequency, it's not well defined. So in this case, I wouldn't recommend using anti-resonance to calculate coupling factor. You should stick to the resonance frequency and using the Q factor and its values, the impedance, the admittance values, which can be calculated from imaginary admittance or impedance there, and let's get back to a linear format that works best here. So kind of working in this way is going to allow you to calculate all the properties despite the unideal characteristics of the anti-resonance point. One of the reasons why we do have more spurious modes with bending transducers is because their assembly relies more heavily and is affected more so by concentricity. So any difference in concentricity, which clearly, the disc is in front of me, it's not concentric. The piezo is not concentrically bonded with the brass disc shim, just due to this manufacturing use case. So that does cause additional resonant modes, and sometimes you'll have more spurious behavior than other times. It can be a way of saying not to use a specific transducer if it doesn't meet a certain specification. Like if there was a spurious mode right on top of the resonant frequency, the impedance would be significantly higher, admittance would be lower, there'd just be less energy transfer if that occurs at the resonant frequency itself. But the fact that it occurs at the anti-resonance frequency is sometimes just a nuisance for analysis, but it also can cause inconsistency as to where that spurious mode occurs. It may occur closer to the resonance frequency at times, and thus degrading or channeling that energy in an unproductive, inefficient manner for the use case of our transducer. Next, we'll take a look at the piezo speaker, which will be another bending transducer. And this is a loud guy, because it has a cone attached. It's very well coupled to the external environment. We'll do that 1 kilohertz to 1 meg again. Step size of 1,000, and let's have some fun with it. And I probably want to just realize this and the traditional absolute impedance and phase. And let's just make this logarithmic for obviously this last portion is slightly error prone, probably due to the noise of the signal measured here. So let's focus our analysis all the way to 200K and see that if we have any resonance modes. So there's apparently one here at 100 kilohertz or something, and there's a couple on the lower end here. Because of the coupling with the cone, any resonant activity is going to be more significantly damped because now it's pushing against the air much more efficiently. So the damping is apparently also increasing. So I just want to take a look at this 20 kilohertz mode there. Let's see if we can't flesh that out a little bit better. So the phase is a really good, an easy way to capture modes that's linear and this is logarithmic. So yeah, so there's modal activity here, and you'll need to use and here you can't really tell the resonant frequency. It's not the minimum impedance. It doesn't correlate to the it doesn't line right on top of the real admittance, which is the power dissipation or the mechanical resonance of the system, just due to the high amount of parallel capacitance. So there are several resonant modes here which occur, and after each of these, the speaker will be loudest at those frequencies. So potentially you could use this at 20 kilohertz to produce 20 kilohertz sound. It's not precisely optimized for that. This is a speaker, so it's best as a wideband. It's working at similar amplitudes, or at least a high enough amplitude at a large frequency range. Opening this back up here, just gonna put that at 1000. So this is clearly a mode at 4K. That's the 20K mode we analyzed. The 4K one seems to be larger. So if we were, let's say, having this device in production, we can use this frequency. Let's go to 3000 to 5000. We can use that frequency as a quality control method. It's analysis there. It's very loud, even with this 2-volt excitation. And even with 2-volt excitation, it's not going to be all those 2 volts are not getting to the transducer because it has a higher. It has a comparable impedance to the driver, the low power driver I'm using. So this response can be used in order to judge the consistency, the quality. The coupling can be used to determine the dynamic properties in order to get consistent sound and performance, actuation performance, even for lower frequencies than the one being analyzed. The one being analyzed is 3.8 kilohertz, although for lower frequencies we'll also be able to make judgments on how well this transducer is working. So this brings us to a close of analysis and kind of demonstration of the ultrasonic cleaner, the surgical instrument, the range finding device. We had the disc, the bolt clamp Langevin transducer, the buzzer, and the speaker. So all of these have kind of some interesting behavior. There were both bending type, longitudinal, and what I'll call radial, but I really wanted to highlight measurements of ceramic samples. The one thing I just remembered that I forgot to do was look at what happens when you have the piezo ceramic, but you don't clamp it right in the center point. So I just wanted to demonstrate that and how important kind of holding your ceramic right in the center with one of these fixtures is, and you may need to iterate on how you hold it. So the way usually transducers themselves are held on foam. When you are testing something like what I'm showing here, or on their side, or if there's actual clamping point, you can measure it in that way. So we have our ceramic disc, and we had that resonance at about, well, let's just find it again. Let's put in 100 kilohertz here. It's 100. Can't hear anything. Well, because it's not. So we have this point, and let's just do this. Let's start from 200 and go to 260. And as an actual company, if you have a company, you're particularly using only a couple of different settings. You're not going to be hunting around for settings all of the time. You are going to be focused on particular transducers with particular frequency ranges, analyzing particular results. So it's not such kind of a jumping around activity. So this phase kind of bend, these are actually spurious resonance which occur due to the holding of the transducer, and potentially also due to material non-uniformities. You'd like to think your material is exactly the same all around, but that's not true. Due to the manufacturing process, the process of pulling, there's electrodes applied. There's even, sometimes the lack of electrode is used to designate a positive or a negative symbol, just showing how the pulling process occurred. So this is our baseline, let's say. So we're at 212 kilohertz and 3.55 ohms. In this case, I definitely probably would want to use short circuit calibration. So I'm going to do that because I haven't done it already. Compensate. Now I'll go ahead and reload it and test that again. When measuring impedance levels like lower than 10 ohms, then short circuit calibration is going to be a good idea at that point, or if your cabling is not good. So I'll go ahead and redo that measurement. We seem to end up with perhaps a slightly lower impedance. There's still these curvature points here at which do signify, again, either material non-uniformities, or they can be also spurious resonances due to how we're holding or how it's being electroded, or how it was electroded. So we have 3.99 and 212 kilohertz. So I'm going to really put this off center right now. Now it's about 1/3 of the way down, the electrode. Instead of holding it in the center, I'm holding it 1/3 of the way down between the two pogo electrodes. And we'll just run that again. So basically 4 ohms. Let's just think about 4 ohms. this what this shows is how you are holding the crystal extremely changes the results. The result before was 4 ohms, now it's 10. So the impedance jumped by a factor of 2. We see a lot of spurious behavior, which is going to be a large contributor to this incorrect holding. It just generates other modes of operation due to holding it in that position. It's semi-clamped. There's some stiffness involved with clamping, and many factors then come together to cause spurious modes and hence large and more damping, which causes a larger impedance and inconsistent results. So to get in order, and remember the previous result was 4 ohms. So let's see how well I can do. It's best to have a manual or like a fixture to ensure that you're getting the exact same place. I don't have a fixture for this exact shape and geometry, but if you're doing this, if you had this size crystal for your production operations, you definitely want to do that. You definitely would want to get a fixture to hold the ceramic in exactly that right point. So remember the first result was 4 ohms when I tried to put it in the center. Now it's 4.1. So that's reasonably consistent there. But it also goes to the fact that you may want to include in your test plan to load and reload your sample if it is again dependent on how you are holding your material.